Now, let's talk about neuroplasticity. Lloyd mentioned Donald Hebb in Montreal, who was a psychologist that was working with Wilder Penfield, kind of like the major neurosurgeon at the time, back in the late 40s. In fact, it was Scoville who did the neurosurgery on HM, or Henry, that consulted with Wilder Penfield, who did all this incredible research around locating memories and all that by stimulating areas of a person's brain. Well, Donald Hebb was working with him, and notice that, you know, when he took rats home and they brought him back, you know, the next day after his kids played with him, those rats seemed to learn more. They had more stimulation, and that got him thinking, you know, that maybe there's something going on in their brains. Maybe if we teach them something over a period of time, they're going to have maybe denser areas of those particular areas of their brain. So he kind of, in many ways, coined the term, but didn't actually say cells that fire together, wire together. We now kind of think of that as kind of a mantra. What does that mean? Well, there are a number of different types of neuroplasticity. It's not all about just making new connections between neurons. That's kind of like the general idea. You know, every time you form a new memory and you strengthen that memory, you're forming and strengthening a synaptic connection. But it's also about dendrites blossoming and having more dendritic connections. Before neuroplasticity, back in the 80s, I was fond of talking about dendritic arborization. And I had some old friends who were then in their 70s who were just really inspiring to me. They bicycled up above the Arctic Circle in Finland and been to 80 different countries. And I would say that they and my father, who was very much like them, were examples of dendritic arborization. Always thinking, always making new connections, those dendrites reaching out and making contact with other neurons, because of thought and because of stimulation. If you want to cut those down, as we now know, when you drink alcohol, it's not like you're just killing a neuron, you're actually shriveling up the dendrites. So in a sense, you're impeding neuroplasticity. So it's not just making new connections, it's also dendrites going out and blossoming and making new connections, as well as including neurogenesis. Now, remember I mentioned that we all probably grew up in psychology thinking that as many neurons as you're ever going to have the day you're born. When we know now, through research down at the Salk Institute with Fred Gage and others back east, that new neurons can develop specifically in the dentate gyrus of the hippocampus with stimulation and, interestingly, exercise, through what we now call sort of miracle grow, which is really brain-derived neurotropic factor. So you want to exercise, and you have to do it volitionally. In other words, not just be chased, so to speak, but go out there and I'm running because I like to run, so to speak. You can make new neurons in your hippocampus and accelerate your cognitive abilities. You just don't want to do the studying while you're running. Wait about an hour. So what you do with neuroplasticity is you increase the receptor density, you upregulate their activity. This is a pretty complex process. You change the shape and the structure of those synapses, providing, of course, that they are pliable enough. I mentioned omega-3, for example. Well, you got to have a good lipid base in here to help you make new connections. Your neurons have got to be pliable enough to make these connections. Well, what happens if we eat too much trans fatty acids and saturated fat and so on and so forth? As a result, your neurons get kind of stiff and rigid. Can't make new connections as well. So diet is critical for neuroplasticity to make new connections between the neurons. These are the classic examples of neuroplasticity. To be a cabbie in London, you must go through a school. Can you imagine that? Go through a school. and sit there and learn about not only how to interact with customers, but also where the various streets are in London and how to navigate and everything. Then after you do that, you're out there navigating through London. Well, researchers at University of London have taken a look at these folks' brains. And sure enough, it's interesting that their right posterior hippocampi are larger than controls, and proportional to the number of years of being a cabbie. What does that mean? Well, of course, they're having more access to right posterior parietal areas, spatial relationships. This can happen over a short period of time, like people that are taught to juggle seem to have more neuroplastic growth oriented towards the areas of the brain in the sensory motor strip that handle the juggling. Then 3 months later, go back to baseline again. Musicians, violinists, who have incredible dexterity and sensitivity for their fret hand. Those areas of their brain corresponding to those fingers are larger than us. Anybody play the violin here? So all of us. In contrast to the bow hand. And then finally, Braille readers. Their reading finger, that area is larger as well. So neuroplasticity has a huge amount to do with what parts of the brain that get enlarged and denser. This is an example of hippocampus neurogenesis that I mentioned earlier. And I think that we're on the crux of being the consumers of a wealth of new information, because this whole field is just moving so quickly. How can you maximize neurogenesis? Think of it. All the people that are paralyzed, waiting around for some miracle cure. Well, right now, most of the research, of course, is on these two areas, the hippocampus and the olfactory bulbs in pregnant women. Why does that make evolutionary sense? Well, certainly with pregnant women, you sense a smell and wondering what's going on. That's critical. Well, the hippocampus, our memory system, is that important to our survival. And here is Miracle-Gro. Amazing stuff. It not only helps with neurogenesis, but also neuroplasticity and the myelination process, so critical for the conductivity of neurons.